Hello, so this is the video presentation for the Physics 115 motor project. My name is Trevor Brown.
My name is Rasapon.
My name is Anika, Larson.
So how this presentation is going to go is we have a series of slides that run through the questions that are required of us. Also in this video includes slow motion capture of the motor actually running.
For question 4a, it's necessary to have insulation because it prevents electron from escaping the wire, which maximizes the current in the loop, and it provides faster rotation speed.
In order for the current to come through the two metal beads into the coil, we had to strip the insulation off of the same side of the wire on each of both sides of the coils, so that there would be an opportunity for the current, for the voltage from the battery to come through the wire.
Yes, and to add to that point, when we strip the insulation off the wiring, we actually only strip half of the insulation. The reason for this is because if we were to strip all of the insulation off, the normal generated by the wire would have a torque force towards the magnetic force generated by the magnet. And if there was no insulation, they would meet each other, become parallel, and the torque force would stop, and so the motor would discontinue to run. However, by only stripping half of it, we have half of the rotation having a torque force exerted on it, and then the other half doesn't have any torque force exerted on it. And so what occurs is when it's on the insulation side, there's velocity momentum generated by the torque force, and so it allows it to continue the rotation, and the motor can continue to run. In the next slide, we're going to talk more about the force equation.
So Ampe's law is the law that describes how the interaction between the magnetic field created by the coil and the magnetic field created by the magnet can generate the torque force that causes the coil to spin. The torque force on the coil is proportional to the number of loops in the wire in the coil, the current through the coil in amps, the area of the coil, the magnetic field strength in Teslas of the magnet, and then sine of theta, where theta is the angle between the magnetic field and the magnet, and a vector that's normal to the flat plane of the coil, so the induced magnetic field of the coil. And the magnet's interaction with the wire is determined by how the direction of the magnetic field of the magnet intersects with the magnetic field that was created by the current through the wire. And not only the direction of those two magnetic fields, but also the angle at which they intersect. So for the direction, our magnet can be placed either north side up or south side up. And if it's north side up, the magnetic field that goes through the magnet is going to be directed upwards. And then the battery that puts voltage into the wire and sends our current through the wire can be oriented so that the current is either traveling clockwise around the loop in the wire or counterclockwise. And if it's oriented so that if you are facing the coil, it's traveling clockwise, and the magnet is directed so that the north side is up, the wire loop is going to spin away from the viewer in order to minimize the angle between those two magnetic fields. And that's how we oriented our motor. So in the first video, you can see that when the magnet is oriented north side up and the battery is oriented so that it's traveling clockwise, the coil spins away from the viewer. And in addition to the directions being important, the torque is maximized when that initial angle between the two magnetic fields is 90 degrees. And so one way to adjust whether the strength of that torque force is to move that magnet back and forth. And you can see that in our video, we placed the magnet directly underneath the coil so that the angle between those two magnetic fields would be as close to 90 degrees as possible.
Okay, so in this next slide, we're going to talk about attempting to optimize the speed. So we were given a standard length of wire that was 2 meters long, and according to the equation, there's a relationship between the number of loops and also the area that the loop itself makes. And so, yeah, according to the equation, if you increase the number of loops, it'll increase the torque force. In addition, if you increase the area of the loop itself, it also increases the torque force. However, because we have a single length of wire, increasing the number of loops means that the area will become smaller, and inversely, if you make the area larger, you'll decrease the number of loops that you can create. While it's possible to calculate the optimal ratio between the loops and area, it is more practical in our case to just experimentally adjust variations of number of loops and area, and eventually we arrived at our current rotational speed, which we calculated to be about 4 rotations per second. And here's a video looking at, once again, like the speed of the motor. The way we calculated this is we used a slow motion camera on an iPhone, and we found that it speeds, I guess it decreases the speed to 1/4 of the initial speed. So we calculated about, in this video you see that there's about 1 rotation per second. And so we just divided, or I guess we multiplied that number by 4, and so we got it eventually the rotational speed of the motor in this case to be 4.12 rotations per second. Okay. And so this question, I guess, in terms of predictions on which way the motor will spin, it actually...
Yeah, this is the predictions about which way the motor will spin. So some different ways to change the direction in which it would spin would be to change the magnet. So in the way that we had it oriented in the video, the north pole of the magnet was upward and the current was traveling clockwise, and as we saw the wires spin away from the viewer, in the square below that, you can see that having the current clockwise and the south pole of the magnet upwards would cause the wire to spin towards the viewer. So you could invert the magnet or hold it in a different position. If we reverse the 2 leads to the battery, such that the current was going counterclockwise, but the north pole of the magnet was still up so that the magnetic field was directed upward, then the wire would spin towards the viewer, and if those leads were kept counterclockwise but the magnet was inverted or moved, the wire would spin away from the viewer again.
All right. And lastly, I'm going to talk about a mechanism by which you can calculate rotational speed, rotational velocity, and this is by using a strobe light. So what you can do is if you have an object that's rotating, you create a mark on the object, and then you decrease the line in the room and put a strobe light on it, and you keep the motor spinning at a constant velocity, and then you adjust the speed or the intervals at which the strobe light is flashing, and you adjust it to the point at which the mark on the spinning object ceases to move, because at this point that means that the rate of flashing, let's say like it's like 10 flashes per second, equals the rotations per second on the motor, and so you can easily calculate from there the rotations per second. Yeah, so I believe that's it. So hope you enjoyed the video, and please let us know if you have any additional questions.